Hello everyone. So today we are continuing the column chapter. So I am going to start. There will be at least 3 videos. The first one there are some theories, and then I'll solve a couple of problems in the class. So I can try to start writing. Yeah. So as we discussed earlier, as I discussed earlier, there are two columns, two types of columns. One is tight column, and the other one is spiral column. So what is tight column? Tight column is there's a beam, there's a column, and this is the rebar, and then there is a tie, and then there is a tie, and there is a tie, and this is the tight column. And the spiral column is this is the concrete, and then there is a longitudinal bar and longitudinal bar, and the spiral column is like a spiral. It's not. It's the same spiral continuously. It's not a separate one tie bar and one tie bar and one tie bar. So this is spiral, and this is a tie. So as I solved one problem in the last class, so I'm writing the equation. So this is only for axial load, no moment, only axial only, no moment. If there is no moment and only axial load, so then these are the equations. So the equation is P R max equals to 0.8 P R O equals to 0.8 alpha 1 FC FIC F prime C A G minus A S T plus phi S F Y A S T. So this is the concrete part and the bracket close. So the first part is the concrete part, and the second part is the longitudinal rebar. Longitudinal rebar. Still longitudinal rebar. So the first part is this part is concrete, and the second part is steel rebar. And the equation for spiral column is P R max. See the difference? 0.9 PRO. So the factor is for tight column it's 0.8, and for spiral column it's 0.9. So the factor is different. So PR max equals to 0.9 PRO. So everything else is pretty much same. Alpha 1 phi C F prime C AG minus AST plus phi S Fy AST. So this is the steel longitudinal steel rebar. Please note that this is not the tie or spiral. This is the longitudinal bar. This one, this long bar, vertical, longitudinal, vertical steel rebar. And these are the equations for only axial load with no moment. Now if you go to the next slide, just trying to do it a little differently. So if I now go to the next slide, so I'm just now showing some of the theories, basic theories. So as I said, first one is for tight column, the factor is 0.8, and for a spiral column, the factor is 0.9. And some other factors for concrete, phi c is 0.65, and for a steel rebar, phi s equals to 0.85. And then there is we will also need a beta 1 factor occasionally, that is 0.9. And we'll also use the alpha 1 factor, which is 0.8. So you need to remember all of these factors. These are irrespective of, this is for concrete, and this one is for steel, rebar, and beta 1.9 and alpha 1.8. We also need to know the epsilon c, which is strain in concrete. So epsilon c equals to epsilon c max, like we need to consider the maximum value, and that value is 0.0035. And what else? We can also consider. We also need to know if this data is not given, then modulus of elasticity, still modulus of elasticity. So that ES value is 200,000 MPa. And occasionally we need to consider epsilon y for steel strain, yield strain, yield strain. So epsilon y is equals to Fy divided by Es. So if our Fy is 400, for example, not necessarily always 400, it can be other value too, but 400 by 200,000. So in that case, our yield, if those are the values, if it is 400 MPa bar rebar, and if it is modulus of elasticity is this, then epsilon y is 0.002. So you need to know all these numbers. So you need to use all of these numbers in the problem statements. And what else? For the column equation, I'm writing the column equation again. So for axial load, the axial resistance or capacity, same thing, capacity, PRO equals to PRCO plus PRSO. So this PRCO is the concrete part, and this is the steel longitudinal rebar part. So concrete is PRCO and the steel rebar is PRSO. S for steel, C for concrete. Okay, so next slide. So I'll take you some other basic theories for column design. One is steel ratio. Steel ratio. So steel ratio is 1% to 8%, which is 0.01 to 0.08. And what is the steel ratio? Steel ratio is AS by BH. And that is the steel ratio equation. And this, our steel ratio should always be between this number according to the code. However, for practical reasons, for practical construction reasons, we can never make it more than 4%. It becomes too much congested. It becomes too much congested. So still ratio rho. So rho is always 1% between 1% to 4%. So our value is always between 0.01 to 0.04. So for practical construction reason, yeah, we can calculate our steel ratio as 0.07, 0.08, but we can never actually construct it, realistically construct it. So therefore, we should always keep our steel ratio rho between 1% and 4%. And few other things. One is our column size. We should always design our column size should be more than 12 inch, at least 12 inch. You should always provide a column dimension. So if this is the column, so our outer concrete dimension should be at least 12 inch or at least 12 inch. And what is 12 inch? As you know, 1 inch is 25 millimeter. So 25 multiplied 12. So our column size should always be at least 300 millimeter. Do not design a column with less than this size, this diameter. Also, we should always ensure that our column strength should be more than the beam strength. So in the ideal in worst case scenario, we will never want our column to fail. If we need to sacrifice one of the two items, we need to sacrifice the beam. So maybe one beam can collapse, but one beam can collapse, but all the columns in a building must stay intact. If we draw a building, so this is so there are four columns total, for example, and then there are beams. So you should always ensure that these columns, so these columns are stronger than the beams. These columns, we should always ensure that our columns are stronger than the beams. So if one in an earthquake or in a blast, if one thing fails, then it needs to be the beam, not the column. We'll always need to design a building such that the column fails at the last thing. Like if the column fails, then the whole building fails. So therefore, we should always ensure that column strength is more than the beam strength. What other things? We should always uh, we can go to the next slide. So for tight, once again for tight beam, tight column and spiral column and tight column. So you always use. So this is a tight column for. So you should always minimum longitudinal steel is at least 4 rebar, 4 rebar, 4 in 4 corners. So if you see 4 in 4 corners, 4 rebar in 4 corners, and then the spiral, as you see, this is spiral is usually circular, and then so this is the spiral. So then there is usually always at least 6 rebar. So minimum at least 6 rebar. So in case of a tight column, we always should use at least 4 rivers in 4 corners, and in case of spiral column, we should always put at least 6 rivers. There is no end to the maximum, but we should use at least 4 river and at least 4 6 bar. And if we need to use, if number of rod is river, rod or river is 28 or 32, then use bundle, use bundles of rods. In that case, instead of one river, we need to use bundles of river. So if it is 28 bars, or if it is a gigantic column and the load is really high, so then we need to use bundles of rod. If it is more than 28, if it is more than 28 or 32 rods, so then use bundles of rods. So those are some of the basic items. And as I told many times, once again, the software used for column design is S column, but it's pretty easy and straightforward. We can use regular software using manual calculation as well. Okay, so I'm going to move to the next video where I'll solve two problems.